So we have begun the chapter on metals, that's chapter 10 in the book. And a quick recap. So most elements in the periodic table are metals and their properties are very different to non-metals, obviously. And some of
Yeah.
the physical properties of metals are that they are good conductors of heat and electricity. So they pass the heat or the electricity along. They usually have high melting and boiling points, and they are malleable, which means they can be made into sheets or hammered or bent into shapes, and that they are ductile, which means they can be drawn into wires. They also have other properties, but they tend to differ from one another. For example, the reactivity with air or water. Right, so sodium, as an example of a metal that is highly reactive when it comes into contact with air or water. Iron reacts slowly. Gold is right, it's unreactive, so right, nothing happens. It doesn't undergo reactions usually. Then we got into talking about the different reactions that metals undertake or undergo. And the first one was the reaction of metals with acids. Right? And so metals, when they reacted with dilute hydrochloric acid, they form metal chlorides and hydrogen gas, which is given off as effervescence. Right? You can see bubbling here. Effervescence,
Sir,
yeah.
I'm sorry for interruption, but um, uh, since metals are like solids, aren't uh, solids are not that good conductor for electricity, right? Since electricity is like a flow type, but solids don't have a flow.
It's not about being solid, right? So if you take a rock, right,
Yeah,
it probably won't be conducting electricity, or wood is a solid, wood is an insulator, right? So it doesn't conduct electricity. It's about, right, what property do metals have that allow them to conduct electricity? And if you recall, when we talked about metallic bonding, I don't know if I can find that over here somewhere. This is bonding. So metallic bonding. Remember we talked about, right, that the valence electrons of metals are all delocalized and they're moving freely between the atoms,
yeah,
right? There are positive metal ions in a sea of delocalized electrons. Those delocalized electrons are what make metals good conductors of electricity, because electricity is a flow of charge, right? And that charge is,
yeah. That was my question. Yeah.
yeah, so the charge that is flowing through metals is via the electrons.
Okay.
Okay, so you don't have electrons flowing through chocolate cake,
Yeah.
right? Or a cookie, and so it's
Yeah.
not going to conduct electricity, even though it's a solid, right?
Yeah. Yeah.
Is that clear?
Yeah. So metals are good conductors because they have positive charge, and so does electricity. That's why they're good
No, no,
conductors.
no, no, not so does electricity, right? So how electricity happens, we'll cover in physics,
Yeah. Okay.
right? So, okay, where was I? Right, so effervescence are the bubbles, for example, you see in a soda bottle, right? So you'll see that kind of those kind of bubbles forming, and then hydrogen gas will be released. Here is the word equation. So magnesium plus hydrochloric acid gives you magnesium chloride and hydrogen. Here is the chemical equation symbol. So you've got magnesium solid and HCl aqueous giving you magnesium chloride, which is also aqueous in this case, and right hydrogen gas, and we balance this out. And this brings us to a reactivity series. So how readily do metals undergo chemical reactions? Not all of them react the same way as we saw, right? Sodium and iron and gold reacting with air or water, their reactivity is different. And so there's a list of elements called the reactivity series, starting from the most reactive, going down to the least reactive. You're starting with potassium, then sodium, calcium, magnesium, aluminum or aluminium, carbon, zinc, iron, hydrogen, copper, silver, and gold. Right, and so that is the reactivity series in general. Right, most of these are metals. You've got carbon and hydrogen sitting over here, right, non-metals. And what we're going to talk about, like what the reactivity series covers, is the reaction with different in different circumstances. You've covered metals with acids. Next is metals reacting with air or oxygen. So metals react with oxygen to form oxides. You've got magnesium reacting with oxygen to form magnesium oxide, balanced equation. It's a white colored oxide. These could be vigorous reactions, right? The metal could catch fire, which does happen in the case of magnesium or sodium and all that, right? The very reactive ones. By the way, the book gives the reactivity series. So if I just take you to the book for a second. Right, so you can see that this is the one you see on screen is the IGCSE book. This one's the O Level book. Okay, and just go up. Right, that is the reactivity series given. You've got the list of the metals, and right, they've given how easily they react with dilute acid and then with air and oxygen, finally with water. So you have that to refer to. All right, same over here, same thing. Right, the O Level book.
Excuse me?
Yes,
Metal can also react with other acids, no?
yes, because see
Other than.
over here they've talked about dilute acids. They haven't mentioned which acid we're we're reacting it with. The example given is with dilute hydrochloric acid. So yes, metals do react with other acids as well, depending on which acid it is and which metal it is. And again, right, talking about the reactivity series, so how readily and easily the metal will undergo the reaction. Okay, speeding up a bit. So we covered the air oxygen one again, right? The ease, I showed you the reactivity series in the book. And so the ease with which metals with react with air oxygen goes down, decreases down the reactivity series. When we're talking about water or either cold water or steam, so the more reactive metals will undergo a reaction with cold water. So you've got sodium and water, and this is cold water. Let me just add that over here. And they will react to give you sodium hydroxide and hydrogen gas, and there is the equation for that. Then,
Sir, which uh, how do they like? The question is how which one of them is easier for the metals to react with?
so right, the ones higher up, sodium, potassium, sodium, and calcium, will react with water directly and readily. Magnesium, iron, zinc, they react slowly with water, but right they react rapidly with steam. So, right, reacting directly with water, the reaction is slow. They're not doing it readily. It might take a very long time for anything to happen. But when you've got steam, so the thing with steam is it's water vapor. It is water obviously, but then it has energy. It's hot. It has energy in it, and so the metal would react more readily with steam. So you've got magnesium, for example, over here, right, reacting with H2O gas. So you've got steam, and what you're getting is a metal oxide and hydrogen gas. Right? Remember, so the products are different. Remember that when metals are reacting with water, you're getting a metal hydroxide and hydrogen gas. When they're reacting with steam, you're getting a metal oxide with hydrogen gas. That's one thing to keep in mind, right? And also, if they give you, for example, what is the reaction of, for example, right? If you go back to the reactivity series, so what is the reaction of copper with water? And you won't have a reaction because copper is way down the reactivity series. It's not going to react with water, right? In fact, if you take a look at the book, what does it say about copper reacting with steam? And so, right, copper pretty much does not react with cold water steam, so you're not going to have any reaction happening with copper at all. Okay,
Yeah.
so
Yeah.
you need to have the reactivity series in mind as well as the different scenarios, right? So uh, that matters. Okay,
In the reactivity series, you said gold is the least reactive. Isn't like, can we just say that gold isn't reactive
yeah,
instead?
it does not react. It's not
Yeah.
reactive.
Okay. Okay.
I mean, you can pretty much boil gold and you can put in boiling water or something, and it's not going to do like it's not going to affect the gold. If have you used aluminum pots?
Yeah.
Have you noticed over time there's like a white crust that forms
Yeah.
in
Yeah.
what do you think that is?
They're burned off.
It's not burned off, right? That is right aluminum reacting with the water,
Okay.
right?
Like, how does metal directly reacts with oxygen?
I'm sorry, could you repeat that?
How can metal like directly react with oxygen?
It can, right? The very reactive metals, as right. So the very reactive metals like sodium and potassium and even magnesium to a certain extent, they are so reactive that they are stored under oil, right? So they are kept away from even the open air, right? If you take sodium out and put it in open air, it is so reactive that it will just burst into flames and react. So just give me a second. Right, so here's the video showing how sodium is stored. It's a soft and reactive metal.
This is sodium metal. It's stored under oil because it's very reactive to moisture and air. Most metals are hard, but sodium metal is really soft, and you can squish it just with your fingers if you squeeze really hard. Metals are usually shiny, and sodium metal is as well, but because it's so reactive, it quickly tarnishes. But because it's so soft, it can be easily cut with a knife, and on the inside, we can see the nice and shiny metal. After only like 10 seconds, it's already tarnished.
You can see how quickly the color went from shiny to dull,
Yeah.
and that is the sodium reacting with the air. Right now, I said there's an explosive reaction, and that is right this.
Hold my breath.
So like only very reactive metals can react in cold water
Hold my
and
breath.
oxygen.
Yes, it is super reactive, right? So as soon as it, like, if there's moisture in the air, right? So the earlier experiment I showed you, right? probably there wasn't a lot of moisture in the air, and so it was fine. If there's moisture in the air, then sodium will react with that moisture as well.
What did the man put inside?
Well, it's either sodium or potassium. So it doesn't say that over here, but the title of the short says sodium and potassium in water.
Hmm.
Right? And you can see the protective gear that he's wearing, the coat and the gloves and the shield. Right?
The first video that you showed,
Mm,
that it turned dull.
yeah.
So when you store it back to oil, it won't go back to
Oh
being
no, because it's already reacted.
yeah.
It's not
Yeah.
going to go back. It's not. All right. So does that clear up your concepts,
Yes.
Haram?
Yeah. Yes.
Okay. So let us return to the whiteboard. Right. After all of that, what we talked about was, right, the different uses of these metals which are based on the reactivity. Right. So that's just some text in the book that you can go over, and then we come to displacement reactions. So displacement reactions are something we came across in chapter 9 when we were talking about the periodic table, and we talked about that in context of halogens. Right. So the reactivity of halogens decreases down the group, and we know that the so displacement reactions for these metals, and because we have the reactivity series, we know that the reactivity decreases down the series. And so you can run experiments in this, right, to check the reactivity of different metals. And what would happen and what you would expect to happen is, for example, you have a right, soluble salt of a metal. So for example, you've got copper nitrate, right? It is aqueous, so it's soluble. And then what you do, you add a piece of metal, a different metal. Now we know copper is way down the reactivity series. It is just before silver. So its reactivity is very low. So pretty much any other metal that you put in other than silver or gold, right, is going to cause a reaction. And the reaction is displacement reaction. So what's going to happen, right, other than right, so you're saying except gold or silver because they are less reactive. You put in the case of copper, right? So copper is the focus. So any other metal you put in, and what's going to happen is, right, you're going to get metal nitrate of, right, plus copper. So the copper will be displaced. It will start depositing as copper itself, and instead of copper nitrate, you're going to get whatever metal nitrate you had. Sorry, whatever metal you put in into the nitrate solution. So, for example, you are putting in zinc, and zinc is more reactive than copper. So you're putting in zinc, and you're adding that to copper 2 nitrate. So the oxidation state of copper over here is 2. And what you're going to end up is zinc nitrate and copper metal. All right.
Yeah. Okay.
How would you notice this happening? So these metal salts, they're usually colored. And so when the displacement reaction happens, you will notice a color change. So what's going to happen over here? You've got zinc metal, which is like silver or gray or something. You put that in. You've got copper nitrate solution, which is blue. And so what you're going to notice is that the blue color disappears. And you get zinc nitrate forming. Right? And what's the color of zinc nitrate?
Brown.
So, right, it is clear or colorless. So you're going to go from blue to colorless. And you're going to have, right, copper metal depositing. All right. And so you're going to have something like brownish, but that will be deposited. So you're going to notice a color change in these kinds of reactions. The color depends on which metal and which soluble salt you're using. Right? Normally you'd use nitrates. In fact, there's an experiment given in the book as well. Okay, let's do the equation for this. Are you up for it? We've got zinc, so that's Zn, that's a solid, plus copper to
Do you
nitrate.
want to balance it?
Oh yes, that is aqueous, and then you have zinc nitrate. It's also aqueous, and you've got copper as a solid. So how would you balance this?
Me or her?
Well, either of you, now there are two of you in class.
I don't know how to balance equations.
Well, then it's just you, so go.
Sorry, what did she say?
She doesn't know what balancing works, so
Oh, I think it's already balanced.
it is already balanced. Right, so you've got right how balancing happens in equations. You see the number of atoms of each element on either side. Right, so the reactant side, this is the reactant side, and this is the product side.
Yeah.
Right, and so you see how many zincs do you have over here? You've got one zinc. How many zincs do you have over here? You've got one. Okay, that's good. How many coppers do you have? You've got one copper over here. You've got one copper over here. Now NO3 is right a molecular ion, so we'll take that as a whole. How many NO3s do you have over here? You've got two of them. How many NO3 do you have over here? You've got two of them. And so this itself is balanced. We don't need to do anything further. If the number of atoms for each element was not the same, then we would have to, add some numbers to either the reactant or the product side to make it equal. All right, so we'll practice that. Okay, now if I take you to the book, right, there is a practical which I'd like to go over.
Practical meaning?
Well, an experimental setup for displacement reactions.
Oh, okay.
So, right, using displacement reactions determine the order of reactivity. Safety, you need eye protection and metal nitrate solutions of, the less than or equal to 1 molar may be harmful. So we know that in displacement reactions, a more reactive metal will displace a less reactive metal from a solution of its sort. We just talked about it. So what are we going to do? We're going to take a dimple tile. This is a dimple tile, right? So it's a slab.
It has holes.
Yes, it's a slab which has holes in it. And so what you're going to do, you're going to put different metals in each of these slots or compartments or whatever you want to call them, right? And you're going to, using a pipette, so that over there is a pipette, you're going to add solutions containing metal, right, nitrates, and then see whether a reaction happens, right? So it is usual to use metal nitrate solutions as they're all soluble, so you can use them in aqueous form, which is very, very convenient. After the metal solution has been added to the metal, you must ensure that the metal is below the surface of the solution and leave time for the reaction to occur. Usually 2 or 3 minutes is adequate. First of all, why is it important for the metal to be under the surface of the solution? Any ideas?
Mm, no.
Gaurav, any idea?
No.
Well, so that it reacts completely and only with the metal nitrate doesn't start reacting with air or moisture.
Okay.
Okay.
Okay. Yeah.
What would be observed if a reaction has occurred? How would we know if a displacement reaction has occurred?
It will change its color.
Exactly, right? So we just talked about that. Now over here you have a table. 5 metals and nitrate solutions of those metals were reacted together using a method that is described. Right? Those were tin, magnesium, zinc, copper, and iron.
But obviously, I don't think copper reacted, right?
Well, you see the table, right?
Yeah. Okay.
The results obtained in the table below, a tick mark indicates a color change, which means a displacement reaction did happen. A cross indicates no color change, means nothing happened. Let's take a look at the table. Now these are the metal pieces and these are the metal nitrates that were added to each piece. So this experiment was conducted like 5 times. First of all, they took a piece of copper and they added copper nitrate to it. So copper and copper, no reaction. The dash means, well, no reaction. It's not that displacement color change didn't happen. Copper is not going to react with itself,
Yeah.
right? There was no color change for zinc, no color change for tin or magnesium or iron, meaning that copper is less reactive than any of these 4.
Okay.
All right?
Yeah.
And you've got zinc. Added copper nitrate. Was there a color change? Yes. You added zinc nitrate. Nothing happened, obviously.
So
Tin.
no color change happened.
Well, it's zinc itself, right? It's not going to react with itself.
Yeah.
It's not that a color change didn't happen. I mean, this is just,
The reaction didn't happen.
well, yeah, right? Tin, there was a color change. So zinc is more reactive than copper. Zinc is more reactive than tin. Magnesium, no color change. So it is less reactive than magnesium. Iron, you do have a color change, so it is more reactive than iron. Then tin displaced copper, did not displace zinc, so you could figure that out. If zinc displaced tin is not going to go the other way. Tin is less reactive. No color change, it's not going to react with itself. No color change, so less reactive than magnesium and even less reactive than iron. Magnesium displaced copper, displaced zinc, displaced tin, displaced iron, displaced all of them. So magnesium is the most reactive of these. Copper is the least reacted. In second place on the bottom, right, is tin. Let's take a look at iron. Iron was able to displace copper, it was able to displace tin. We've got 2 reactions for iron. We have only 1 reaction for tin, 3 for zinc. So I believe the order of reactivity, highest reactivity would be magnesium. Second would be zinc because it's displacing 3 of the metals. Zinc is displacing 4 of them, right? Then iron is displacing 2 of them. That's third. tin is displacing only one of them, so that's fourth, and copper is last because it is not displacing any of the other metals. Does that make sense?
Yeah.
Once again, let's go back to the whiteboard. Okay. What's next? Right. Next is we're talking about how you would identify metal ions.
How you would identify what?
Metal ions.
Okay.
Can you please briefly describe what are ions?
Ions are formed when atoms of elements either lose or gain electrons. Right, so that is part of covalent bonding. Sorry, ionic bonding, not covalent. Right, for example, sodium, it loses one electron, and the recording for this is available on my playlist. You can refer back to that. And so sodium, right, has 11 electrons. It loses one. Why it loses one, I'm not going to detail for that. You can refer back to that particular recording. Right, so it's losing one electron, and so it's developing a positive charge. So this is, right, a sodium ion that has lost one electron. Chlorine, right, gains an electron, so it gets an electron from in this, right, from whatever it's reacting with, and so because it has one extra electron than it gains a negative charge. So this is right, chlorine ion. So ions are atoms of elements that have either lost or gained electrons as part of the bonding process. Okay.
Yeah.
And metals lose electrons, right? All metals. So sodium is a metal. You take any metal, you take aluminum, it loses 3 electrons. Copper can lose either 1 or 2 electrons, right? Iron can lose either 2 or 3 electrons. So those are transition metals. That's a different story. You can refer to the recording for the periodic table lectures, right? And so that would explain the oxidation numbers. So, right, magnesium loses 2 electrons. So metals always lose electrons, and so losing electrons gives a positive charge, right? And so they always form positive ions.
And non-metals usually gain electrons.
Yes.
Thank you.
Just leave it there in front. Okay. So how do we identify metal ions? Uh, so what we do is that we take a metal, a soluble salt of a metal, why are we saying soluble metal salt? Because not all metal salts are soluble, as we will see, right? And we add uh, sodium hydroxide. And so what we would get is an insoluble, right, precipitate of metal hydroxide. And along with that, we would get right? Well, that's basically the focus. We'll get another salt, a different salt that will most likely be soluble. So an example is taking iron 3 chloride. We just talked about iron having either a 2 or 3 oxidation states, so either losing 2 or 3 electrons. Iron 3 means that it has lost 3 electrons in this case. Iron 3 chloride, and you are adding sodium hydroxide to that, and what you are getting is iron 3 hydroxide just iron 3 hydroxide and sodium chloride. And the iron 3 hydroxide, this guy is insoluble. And so what you would see is that you would see it precipitated.
Can you please explain it again?
Right, and this insoluble metal hydroxide is often, this guy is colored. So depending, so whatever colored precipitate is forming will help you, the color of the precipitate will help you identify which metal was in the solution that you were testing.
What does precipitate mean?
Precipitate.
Yeah, what does it mean?
Right, precipitate is a solid that forms after a reaction of liquids, and so it's a solid. It's not dissolving in the liquid, and so you've got this liquid and you've got these solids that are forming and maybe settling at the bottom of the test tube or suspended, or depends. So in this case we have metals. You've got iron chloride, which is aqueous, it's a liquid. You've got sodium hydroxide, that is also a liquid. So let me write that out. FeCl3, that's iron 3 chloride, that's aqueous, and you have NaOH, which is also aqueous, and what you are getting is
What does aqueous represent?
aqueous means it is liquid.
Liquid solution, I guess.
Yeah. FeOH3 is solid. Plus NaCl aqueous. Okay, so you've got these two aqueous solutions, sodium hydroxide and iron 3 chloride. And when they're reacting, you're seeing that the solid is forming. So when the solid forms, that is called a precipitate.
Yeah, okay.
Okay.
Yeah.
Now, the fun part. Balance it. Aram, you can try as well. Look at each in turn. So let's take a look at iron. Fe is iron. How many do we have on the reaction side? 1.
Oh, yeah.
How many do we have on the product side?
1.
1. So Fe is fine. Chlorine. How many do we have on the reactant side?
1. yes, sir.
Okay. So you got 3 on the reactant side. How many do you have on the product side?
1.
1. So there's obviously a difference. So how do we fix that? Sophia?
Um, we put 3.
We put 3 here.
Yeah.
That would give us 3 chlorines, but now it's also giving us 3 sodiums.
So we're gonna put 3 sodium on the reactant side.
Right? Now we got 3 sodiums here. We only have 1 here. We put 3 here. So now we got 3 sodiums here. But now we also have 3 of the OH. Remember, the OH is molecular ion.
Which automatically balances it out.
And we got 3 over here as well. So now it is
Balanced.
balanced. Did you follow that, Varam?
Yeah.
So, right, there's another thing that they're giving over here is the ionic equation. And the ionic equation is only going to deal with the ions of interest. So what we're interested in is the iron and the hydroxide, which gives us iron 3 hydroxide. Right? Because it's iron 3, what will the ion of iron look like? Right?
Yeah.
And then you've got OH, which has a single negative charge, and you've got 3 of these guys. Right? And both of these are aqueous. And you are getting FeOH3, which is a solid. Alright, so what's an ionic equation? It looks at the ions of interest, right, and how they react. In fact, if I go back over here, we have an ionic equation for this as well, the displacement reaction. So, right, how is that going to, what's that going to look like? You've got elemental zinc over here, so that's Zn, right? Elemental zinc has no oxidation state, so it's basically 0. You don't need to write 0, but just to tell you. And you've got copper 2, so that has an oxidation state of +2. Now you've got zinc and elemental copper. So that's the reaction. So basically what's happening is, right?
The exchange.
Well, yes, zinc gave electrons to copper.
Copper.
And so this is a redox reaction. Right? Zinc is being oxidized and copper has been
Reduced.
reduced. Right? Why? Because zinc has lost electrons or its oxidation number has increased, however you want to take a look at it. Right? And so that is oxidation. And copper has gained electrons or its oxidation number has decreased, it went from 2 to 0. And so that is reduction.
Okay.
Alright. You want to continue?
Um,
What happens is, right, this happens when you add a small quantity, right? All of this happens when you're adding a small quantity of sodium hydroxide or alkali, right? We haven't done acids and alkalis, of the next chapter we'll do, but I'm just throwing that in there, right? So, okay, what if you add excess? Excess meaning you add a lot, you add more. right? And so when you add more of that, right, the precipitate in most cases, it ends up dissolving, so it goes back into solution. Right? In most cases. So for aluminum and zinc, right, except aluminium and zinc, the precipitates do not even in excess. There's a table given in your books, which was shared out with you as well, so going back to the book.
Can you please explain it again, please?
Which part exactly?
Identifying metal kinds.
See here, right? When we are testing for the metal ions, right, we are adding alkali, right, hydroxide. We're adding an alkali in this case sodium hydroxide. What we're getting is an insoluble metal hydroxide. We talked about iron chloride and sodium hydroxide, iron hydroxide, which is insoluble. So it's precipitating. You can see that cloud, right, precipitating, and right, a solid. If you add excess, in some cases the precipitate dissolves in excess hydroxide owing to the amphoteric. So I'm going to what amphoteric is, right? Not now, but owing to the amphoteric nature of the metal hydroxide. Okay, and here's the table. You can see they're giving you these various metals, and when you add a few drops of sodium hydroxide, aluminum gives a white precipitate, calcium also gives a white precipitate, chromium 3 gives green, copper 2 gives light blue, iron 3, sorry, iron 2 gives also gives green, right? And iron 3 gives red brown, and zinc also gives white. What happens when you add excess? Well, aluminum is soluble in excess, right? Calcium is insoluble. Chromium is also insoluble, right? Precipitate for the copper 2 is also insoluble, right? And iron 2 is insoluble, iron 3 is insoluble, and right, zinc is soluble. So I think, right, right. So I actually, in my explanation, I think I mixed that up. Let me go back to that. So, my bad. So let me correct this. Right, most remain. So we're talking about the precipitate over here. Remain insoluble, in fact, right, except aluminum and right, zinc. So I got that the other way around. Apologies for the confusion. Anyway, is the concept clear now?
Yes.
Aram?
Yes.
So you're welcome to following topics, the extraction of metals and right, extraction of iron in particular, and then corrosion and prevention
Yeah.
of corrosion.
Yeah.
Those I think we'll be able to cover the whole thing tomorrow.
Yeah.
So we'll be done with this chapter tomorrow, and then we can start moving on to the next chapters. Alright, so do review it from your textbook. If there's still any confusion, you can ask me next time. I'll try to bring for clarity. Yeah, that's all for today.
Okay. Allah Hafiz.
Allah Hafiz.